Hello everyone, this is Rahul Mahajan doing this video after a bit long time, but this is like next in the series of my work on sharing with the larger community on artificial intelligence. Today I'm going to specifically talk about the work that's happening in the generative networks in the AI space. This is a fast evolving field. A lot of advancements have happened. Some interesting stuff has recently come out this year from OpenAI. That work DALL-E, some of you would have surely heard about it, read about it, and then also experienced the whole thing. I thought let's little bit go deep into the what's happening behind the scenes from a network architecture point of view, little bit from a methods point of view, and talk about where are we headed, what are the opportunities for us from this point onwards, and what are the kinds of also the promises and limitations that we should be clear, so that we can obviously improve this further. With that, let's go deep into the next step. So specifically the generative AI space is not something which is new. This has been kind of in discussions almost all the same time when image nets and convolution neural networks came in 2014-15. At the same time, a lot of work also started on generative AI space. Some of the initial inspirational work came in from Ian Goodfellow. The gentleman, there's a story behind it, interesting story behind it. The person was already working for a leading company and kind of working on the generative AI along with his friends. One day they happened to be in a bar, kind of discussing some of the issues they were facing in terms of handling large-scale data around images and so on, and the kind of problems generally networks have. The friends of Ian talked about the issue they are having on this whole space, in the whole large-scale image generation space. And Ian had an opinion that this is not a programming problem, this is more of an algorithm problem. And later that night he worked on it and came out with some of the work that we now see as a kind of a initial fundamentals of generative AI. So essentially what happens in this whole thing is there are two networks which are working hand in hand. One, there are two neural networks, and this is very unique. Generally, we would have one neural network. In convolutions, you typically have layers of neural networks, but essentially one logical neural network. But in case of GANs, there are generator and discriminator, two different networks. Generator is, and again, there are two stages. Typically in almost all neural networks. One is where you train the network through data sets, and that's where discriminator is the one which typically looks at the data and tells on the quality of data set. The other is the actual execution phase, where in this specific problem the goal is to generate a good quality image from a random text, or not from a random text, from a random noisy data set, or from a text input. So there's a latent space, and generator is the first step in the actual execution which gets kicked in. So the input comes, a noisy input reaches generator, either by mixing noise or by starting with a noise. So we start with the noisy data of an image, and generator is supposed to, as a step number one, supposed to generate better versions of it. So the neural network has already been trained, and generator generates these images out of the generator network. Discriminator on the other side is a second neural network which is kind of looking at the outputs of this generator and taking real samples, and also kind of using that to inform whether the generated image is good or bad. Once this whole data set is trained, then typically generator becomes very, very powerful, and it becomes hard for discriminator over the time to differentiate between what's fake, what's real, essentially generating a very good quality images. So that's essentially two parts to this whole algorithm. That's how it started. As you can see on the left side, that's what generator does. Discriminator is around taking the real data and kind of classifying outputs of generator into good and bad, which is this whole 0 and 1 kind of an output. And over the time, generator becomes very important. I like to give the credit to, at least for the images from a blog from Lian Bag, and people who are interested to go further deep, they can read about it. So GANs are not the only network which generate images or generate content. There are other neural network architectures which are also kind of there, which are equally interesting to look at, and they are also capable of generating data. The other architecture is, which is very famous, is this whole variation autoencoder. These class of it's a class of dataset which is it's a class of an architecture which is kind of responsible for again responsible to generate the goal is again same to generate the images. It doesn't works like a GAN. In this case, what happens is there is at least in the training phase, we typically use training data, make it go through the encoder. Encoder essentially converts this into an image embedding, kind of a latent feature, which then goes to the decoder, and then decoder, based on this embedding, reconstructs the visual field. So this is the way it works. And as you can see, in an actual, we generally just go with we generally go with input to the one part of the architecture, and we give it to decoder, and decoder once trained is able to generate good quality images. Now, variational autoencoder are slightly different from the previous GANs in terms of they provide a probabilistic manner to describe the overall latent space compared with very, very deterministic mapping. And in this, a lot of ways becomes also kind of limitations of both GANs and VAEs, that one, they are slow to train, they take a lot of time to train, convergence is hard, we see vanishing gradient issues, those kind of things, and also they are not very loyal to the image. We get variety of kinds of outputs which generally are not exactly matching to the core data, the input data, and there has been kind of these have been the kind of problems. So GAN, which had two neural networks, which was very unique in its time. VAE, which has more of an encoder decoder architecture, and I talked about the problems. Now, OpenAI Dall-E team came out with a very, very different, interesting style to look at this, especially the Dall-E-2. And Dall-E-2 typically looks this whole problem in a very interesting way. It uses a diffusion architecture. But essentially, before I talk about the diffusion architecture, let me first describe what's Dall-E-2. So typically, you can go and give an input text. So things like a corgi playing a flame throwing a trumpet, trumpet. Let's say that's the image you want to generate, and so that's the input that goes to the encoder, and that's step number one. So there are two typical algorithms: the clip algorithm and the whole glide algorithm. So the clip algorithm typically kinds of deconstructs the whole text embedding, and goes and find the necessary does the match between the text embedding and the image embedding, and gives this as a prior to the glide algorithm, which is the bottom part of the architecture. And the glide algorithm is a very intelligent diffusion algorithm. It's a class of a diffusion algorithm which then along with noise generates the final output, where we see that's the output that we get. Now, what is diffusion algorithm? How are diffusion algorithm different from what we saw in GANs versus VAE? let's go a little talk about that. Let me talk about that. So typically a diffusion algorithm is slightly a modification of VAE or and even GANs. In GANs, if you remember, we have two neural networks. One is kind of generating, the other is discriminator. VAE on the other side has this whole concept of encoder and decoder. What diffusion does is it looks at the problem in a very different way. Think of two processes. One is this forward process, which is typically you start with an image, convert that to a noisy data set, and then based on the noisy data set, the algorithm, the architecture is trained, and that's the reverse process, which you see on the right. From a noisy set, regenerate the actual image, and this whole thing happens as a diffusion. So which means if you think it from a Markov chain perspective, I'll talk about Markov chain as the next thing. Think it from a Markov chain perspective. You start with at least in the reverse process, you start with a noise which is kind of let's say sample t, because this is 0 to t in a way, and what we're trying to do is go back to x0, but in now do the reverse process, which is the and then probability of moving from one step to another step is what we call as p0. Probability of moving back is what we call as q, and essentially trying to find this whole do this whole process at the same time. This is what diffusion process is all about. It's important to understand what's the Markov chain, how the probability are typically relevant in this scenario, how does this whole shift happens from step one to the next step. So Markov chains are nothing but, and we are going to only talk about the first order Markov chains, which is what we use. So there are typical states in a typical Markov chain, and you can think of states from 0 to t, and ones on one direction is typically called as with donated with probability of p. The probability on the other side of moving from a previous stage to the next stage is donated by q. So the notations are typically, for example, what's the probability of moving from n-1 to n, given all the steps have happened from q1 to qn-1. So and this is what is in a simple way, because it's a Markov chain, you don't have to worry about what happened behind n-1. You can forget all behind the scenes. So hence we typically say is this is whole represented as probability of moving from n-1 to n. Now typically if you this is first order Markov chain, then there are second and third order Markov chains, essentially where even the second and third stages, previous stages are relevant. So an mth order Markov chain typically would have in the same notations, for n to happen it has to look back m stages. So hence from n-1 to n-m states matter, and all the probabilities have to be considered in a joint way. So what does it mean? So typically the final probability to reach a specific state is going to be a joint probability of all the previous stages, and that's how think it from a Bayes algorithm of conditional probability, and we will end up with multiplication of all the different stages. So probability of first state happening, and then second state happening based on the first state, third state happening based on the first and second state, and the nth state happening from 1 to n-1, and that's what typically is donated by this whole projection of all the probabilities, where I is equal to 1 to n. So this is a very, very fundamental Markov chain concepts that is important, because one of the things we are going to do is also look at the paper in terms of how these things have advanced over the time. Other important step is to also understand KL divergence, which is another important concept in this diffusion algorithm. KL divergence is typically useful to understand the variation between two probability distributions. So imagine there are two probability distribution. let's imagine they follow a normal distribution. So there's a px, which is one probability distribution 1. There's qx, which is probability distribution 2. Essentially, what we're trying to find is what's the variance in these two probability distributions. Typically, if you want to look at variance, you will typically see the distance, and distance you can think of as let's say there is one distribution can be denoted by x and the other can be denoted y. The distance is typically x minus y. And then we typically try to, if you're talking about distribution, typically we would like to talk about an average. And in case of probability, the equivalent of this is we talk about probability distribution, and we talk about we take logarithmic probability because of just to make sure the smaller values get proper treatment. So we generally look at difference as between two distributions as log of for an ith point, log of pxi minus log of qxi. And given the fact that this has to be done across all the sample points in a distribution, we do a summation, and for a specific point we take the variance by kind of using the probability of that ith point. And we have to take so in a simple distribution we'll typically an average. In case of probability, expectation is the most logical thing to do, because expectation is kind of the outcome what you get after let's say n samples, right? So expectation is the best way to look at the averages, and hence we take an expectation of both the differences of both the distribution, and given we have to do it for all the points, we take a summation of it. Subtraction in logarithmic logs can easily be denoted by a fraction, which is pxi by qxi, and given it's a continuous space, we are not talking about discrete distributions, we are talking about continuous distribution. For the entire distribution, we can easily take an integration of the distribution from minus infinity to plus infinity. So that's how the KL divergence is, and this is going to be very, very useful as we go to the next stages. So let us go back. We talked about what are the Markov chains, what's KL divergence, but essentially we want to understand what has been done in the Dall-E, which Dall-E-2 specifically, which uses a diffusion algorithm. So we'll go back, and the whole idea is in Dall-E what they do is they typically add they start with a noisy data set. Essentially the outcome is to generate the final output. The whole idea is to intelligently mix noise to the data set so that we get the final output. So essentially what you're doing is two parts to the algorithm. One is the whole clip phase. Whatever we type, that gets semantically classified using an NLP, and we go and look for the fragments of the images, and in an intelligent way. That's what clip does. Now we have multiple fragments of these images, and the next step is to intelligently kind of combine them in a creative way, in a very, very unique ways. And the way it can be done is using this whole diffusion algorithm, which is called the version of what Dall-E-2 uses is Glide. We'll talk about it. But now with these all image fragments, we have to smartly combine them to generate the final output. But while we combining them, we also add noise. Now this is where the smartness starts. How do you add noise? You could add all noise at one time. The other option is you add noise in gradual steps. So if I have to add noise in small steps, so that one I can trace during the whole learning process. Because if you add entire noise as if you think of noise as just one big thing, it becomes hard to train. The traceability is too complicated. So what we do is add noise in a Markovian chain process. Across the different steps, we add small beta factor of noise, and then we train the entire neural network both in the forward and the reverse process, so that we get to know uh, the noise distributions at each steps. So that's essentially what we do. I'll talk a little bit about how this paper does, and people who are interested can go deep into this whole paper which came out in 2020. This is the paper title is Denoising Diffusion Probabilistic Models. So what essentially it does is think of noise as a latent variable, PXO, and as we talked about in the whole Markovian chain, the final probability of a given point is nothing but an integration of probability for all the steps of the chain, right, from 0 to t, and that's what we use. So think of joint distributions, and in joint distributions you typically have projections because all probabilities will eventually get multiplied. So from t is equal to 1 to t, which is the first stage, to the tth stage, all probabilities in a projection, and that's what gives you the probability at the tth stage. But then at every stage from t to t minus 1, which is the reverse process, essentially the goal is to and this is the reverse process, right? The goal is to also at every step from t to t minus 1, we essentially want to learn we deploy a neural network in the reverse process from t to t minus 1, right? Essentially we want to deploy a neural network to understand what was the nature of noise that was mixed, and given it's a normal distribution, typically there are two parameters. One is this whole mean, and the second is variance, right? So sigma denotes the covariance matrix, mu denotes the mean, and n denotes a neural network that's gonna kind of learn both the things. So in the reverse process, so the idea is to use the neural networks to understand this whole mu and sigma. Now, what distinguishes diffusion model from other types of latent variable model is how we approximate the posterior, which is in this case q, right? So if p is the original probability from t to 0, q is the reverse probability. So what we want to understand is in a typical Markovian chain, how to gradually add noise, and if let's say the beta is the kind of variance scheduler at every step, we essentially want to compute the coefficient of beta, and that's the whole goal of the training method and the optimization method. Now what you see here is even for the reverse process, we use the same we use another neural network. In this case we take what has been done is we instead of learning the individual step, we try to learn the noise. So the mean has been taken as what you see as 1 minus beta square root. This is not that complicated. So in a typical normal distribution, the goal is you want to find the mean, and we want to make sure it's a normal distribution which is centered at 0. So if we are far from 0, which is, let's say we are at an x point x from 0, and an x is less than 1, essentially we are trying to gradually come to 0, and hence we try to do this whole 1 minus beta x. And we take square root because of mathematical convenience when we do this whole operation. So that's the whole point. But the training is typically performed by using an optimization algorithm, which essentially is nothing but using the KL divergence, which I discussed in one of my previous steps. We try to minimize the distribution between noise distribution, probability distribution variance between the probability, so noise in the forward process versus the noise in the reverse process. Because essentially it should be, if it matches to, if the variance is least, that's where you will get the actual output, right? So the whole idea is to take the is to take a law in a KL divergence format. Take the think of variance translates to log in probability, and take the expectation and essentially try to use this expectation and kind of take a negative log likelihood approximation of this. So that's how we do. If I go to the paper, it's a very interesting paper. Give me a second. So in the paper, if you go and yeah, so this is what I was describing. The paper essentially talks about the same thing. How do you optimize using stochastic gradient descent? I'll talk about stochastic gradient descent, but then essentially use the KL divergence, and using the KL divergence of both the distributions, the posterior and the forward distribution, and try to minimize it and essentially get the beta out of it. Now this is little bit interesting if one has to understand this little bit more deep. One should try to understand how the eigenvalues plays, the role of eigenvalues to kind of derive all this stuff. So but I think not everyone is going to be interested in the maths, but I'll a little bit skip forward. But as I talked about, there are going to be a forward process, there is a reverse process, and typically the goal is to understand the using neural network, the mean and the sigma, and that's the whole process of this goal of this whole paper, which talks about this. There have been further improvements to this whole process. I'll talk about. So the reverse process diffusion is what we were talking about. The goal is to generate high fidelity data, which is same as what we got at x0. Now typically there are advancements in terms of what can be learned over the time. There are variations of different papers over the time. Research papers have demonstrated different kinds of neural network architectures at this stage. Sometimes we try to predict the variance, sometimes we try to predict the mean. In some cases we are trying to predict the overall noise. Essentially the neural network follows a unit architecture, which again has kind of encoder type style, where we have initially large number of convolution layers, and eventually we go down and then we again go up. So this is a unit architecture, which is also interesting to look at. And as talked about, there are different papers on how this whole noising process can be done. One of the initial papers was in 2015, which came, which talked about this whole non-equilibrium thermodynamics, and what we are right now doing in Markovian chains is kind of an inspiration from this paper. Then this is the paper that I was referring to, which also talks about the whole forward learning process, the reverse learning process, using diffusion and kind of using neural network to learn the entire noise. Then there are further improvements to this work. There is a recent paper in 2021 and 2020 where we are using probabilistic diffusion model. And there is another recent one where we are talking about how this whole probabilistic diffusion model can even do better stuff. But coming back to the whole point, the glide algorithm, which is used in Dall-E, is pretty interesting. So couple of call outs. for people who are interested into go deep into the glide algorithm. So the unit architecture, typically the goal is we start with an input image, and we want to kind of learn. In this case, we want to learn the noise. So we start with a kind of a input image with a noisy data set, and we want to understand the noise that was mixed to get the output. So that's the goal. So in the clip, what we do as one of the tricks in the OpenAI glide algorithm, we also in this process give an additional embedding of the text that was given as an input, and not just that. And not just the initial, we don't give the input just to the initial layer, but in fact all the layers. So it's a pretty sophisticated guidance in terms of making sure the convergence happens fast. So additional guidance is given to the image encoder, which is FX, by using clip encoder GC. Look at this, right? So this is section 2.4, which talks about in this paper glide, which is a recent paper which came out in 2022. So it talks about diffusion models, how diffusion models have been successful in generating high fidelity images, especially with the guidance technique. This guidance technique to me is very interesting. In a lot of ways, we are kind of in some ways also diverting from the whole learning networks, but that's a different point. Let's ignore this thing. But it's a kind of a mathematical hack which we are trying to do to speed up the whole thing. There are so let's first finish this. So it talks about the section 2.4 talks about the scalable approach using clip as an embedding, and it talks about how the clip embeddings are given to the image embedding. The caption in the clip model, the image embeddings also get the caption embedding, and not just that, the paper also talks about how in the reverse process the mean gradient is also given to the stochastic to the whole gradient descent. This is a technique which is also used in a lot of other algorithms, where you try to give a bit of a momentum so that the steps that you take in the descent stage while optimizing has additional input and guidance from the previous stages. So some of these tricks have been done, and for people to little bit appreciate this, you will have to also look at the whole work that has been done in terms of speeding up the gradient descent using stochasticity, momentum, eigenvalue reductions, and stuff like that. Last but not the least, the Dall-E-2 algorithm also does one more step, hopefully the final step. And in this step, this is section 2.3, which talks about the classifier-free guidance. This is basically what it does is, this is a technique where for guiding the diffusion model, that doesn't require a separate classifier model to be trained. And what we do is we give another conditional kind of a small input. What we do is we train the model one by giving the clip the text caption based encoding, and we also train the other part by giving no embedding. So essentially what we're doing is and then we see the difference. What if we give the caption embedding? What if we don't give the caption embedding? And depending on the difference of these two, one is this with null, one is this with caption, and then we look at the variance, multiply this, use the variance as a stock function, and use this as an input for further extrapolation. Now these are interesting tricks tricks, hacks, whatever you want to call it. But that's all. That's how the whole advancements are happening. We continue to find more and more mathematical ways to speed up and optimize. Uh, so these tricks and hacks are essentially what a lot of these incremental modifications continue to improve, and that's why we see the improvements, because now what we're doing is we are not just letting diffusion process work on its own, we are also giving clip guidance, we are also giving momentum guidance, we guidance at different stages, and making sure the final output comes out very nice. So that's the whole goal. And that's why we see some interesting stuff. For example, an astronaut sitting in a horse. These kind of things can only be done with this kind of smart engineering that's happening behind the scenes. Kind of very interesting in terms of how the whole thing is happening. And yeah, now I'll stop here. But essentially, my goal was to talk about what's the engineering happening behind the scenes, how this whole maths is working together in some ways, and is it a hype? How far it can go? I leave it to you folks to decide. Keep in mind, essentially, what's happening is we are using clip to kind of smartly hunt down the right fragments. We are using diffusion processes to do a very intelligent diffusion process to get the final output. So, how far will these GANs go? Is I think it's easy for us to all of if you know the science, it's easy to us to imagine. There is not a lot of creativity which is happening inside the engine. Just by mixing noise, you can get only this far. So for us to really do something interesting, I think more improvements are gonna happen over the time. But for now, I hope this was useful. I was able to explain a little bit about the engineering behind the clip algorithm, and thank you so much for your time.